Hi, I'm Spencer Lashbrook.
I'm Schwartz.
I'm Hunter Felder.
I'm John Siddiqui.
And we're going to be taking an inside look at the design process behind our FEDD project, the Collapsible Bridge.
As we created our FEDD project, we followed the steps of the engineering design cycle: ask, imagine, plan, create, and improve. In the rest of this video, we will show how we used the engineering design cycle to help us successfully design and create our collapsible bridge.
The first step of the design process is to ask, and the first question we asked when designing our project was what type of bridge to build. We researched different types of bridge structures such as girders, trusses, and arches, and watched previous FEDD videos to see what ideas worked and which ideas did not work at FEDD Day.
As we researched each bridge type, we determined that the truss bridge would be the strongest and the easiest to build. We eliminated multiple different types of bridges as we researched for a good bridge to use. We eliminated girder bridges, arch bridges, and suspension bridges. We eliminated the girder bridge because at this point we had already researched the truss bridge, and we determined that the girder bridge would be too complicated to build and that it wouldn't have as much success as the truss bridge. We eliminated the arch bridge because it was the most popular bridge and a lot of people used the arch bridge in previous FEDD videos. We also determined that the arch bridge would be the most difficult to have success with because it seemed to have a complicated design as well. And then we also eliminated the suspension bridge because it seemed very complicated to build. The ropes seemed to add a lot of weight, and we didn't have anything to suspend the ropes from.
After eliminating other bridge types, we decided on a truss structure because they have performed well in the past and are aesthetically pleasing. We saw a video of a truss bridge that was able to meet all the requirements and hold several people without breaking. We thought a truss bridge would be the best bet for our FEDD project.
The second question we asked was what to build the bridge with. We looked at two main types of materials, aluminum and wood. Aluminum is strong and light, but difficult to work with, and none of us had experience with metalworking. So we decided on wood. Wood is also strong and light, and was relatively easy to build with. We used pine wood in this because its strength to weight ratio is high enough to fit the parameters of the project and was cheap enough to be well within the budget.
So at first we planned to connect the segments of our truss bridge with hinges. This method would enable us to quickly construct the bridge. However, since the hinge would only support a joint on one side, we thought this option would weaken the structure. Later we thought connecting our segments with dowels would be a better solution. This would support the joint centrally and, like hinges, enable us to quickly build up our bridge from a collapsed state.
We invested a significant amount of time drawing out an exact blueprint. We carefully calculated the volume of the bridge, and using the dry weight of the wood we were going to use, approximated the weight of the bridge.
After we agreed on a final blueprint, we bought all the needed materials at Lowe's and began construction on the bridge. We started our design process with the main beam, as we knew this would be the main weight-bearing structure. Once we all agreed on a design for the beam, we started work on designing the truss structure around it. For purposes of weight reduction, we decided on a thinner, lighter design on the truss. Our original intent was to use dowels to facilitate easy assembly. For our design scheme, it ended up making the most sense to use screws and bolts to hold the bridge together instead, and we wanted to retain as much structural integrity as possible. Finally, after we had the bulk of the bridge completed, we realized that our bridge was still significantly below the weight limit. With this in mind, we took steps to make the bridge more secure and aesthetically pleasing, adding diagonal supports to the truss and horizontal platforms on each end of the span to ensure freestanding stability.
So the next step in the engineering design cycle is improve, and when we started building we noticed that dowels would not work. The drill bit was either too big or too small, and the dowels would just not fit correctly.
Eventually, we decided to use notches and screws. However, when we started putting the bridge together with the screws, we determined that the screws did not hold the bridge segments together as well as we had expected. From the screws and notches, we learned that we needed to find a way to distribute more pressure to each joint to make the bridge more stable. Therefore, we decided to use bolts and nuts with washers. By placing a washer underneath the bolt head and underneath the nut, we were able to distribute more pressure to each joint and therefore make it more stable.
We rebuilt and designed the bridge around the bolt washer idea and added more support between each section of the bridge. Then, we sanded it down to make it feel better and wood burned our team name onto it. From there, all we had to do was practice building it in under a minute.
Our bridge met all the FEDD specifications, which are: bridge must be under 5 pounds, hold over 60 pounds, be collapsible into a 1 cubic foot box, cost less than $40, and be built up from a collapsed state in under 1 minute. We won 3rd place in the FEDD competition, holding 100 pounds more than required. The bridge that won was an arch structure connected by pegs. The 2nd place bridge only held 70 pounds, but was an elegant looking truss structure connected by sliding bolts.
In conclusion, we all had a great time working on this wonderful project that helped us develop not only our teamwork skills, but also our practical problem-solving skills. Of course, with more time, we could have produced a more refined product. However, we were all very pleased with the result.
Yeah, for example, building the bridge in a minute was a hassle. Perhaps with more research, we've been able to connect the segments in a more efficient manner.
In addition, we could have created a thin metal sheath to cover the area of the bridge where the hooks would be applying weight. We noticed that when the weight was being applied, that the hooks were digging into the bridge and causing some significant damage. The metal sheath would have served the purpose of distributing the pressure that the hooks applied across the bridge, and therefore we would possibly be able to hold more weight.
Finally, our advice to future E101 students is, watch videos from previous FEDD projects. They offer a lot of insight into what works and what doesn't. Go to the craft center early, there will always be unexpected problems, and really enjoy FEDD. It is a great opportunity to get to know some of your fellow engineering students and take a break from studying.